on. In chapter 6, we've defined how second law of thermodynamics covers certain flip sides that are left out in the first law of thermodynamics. We indicated how this law shows if a process is going to be feasible or not, and it also indicates the direction of a process. And we looked at different ways of defining the second law of thermodynamics, one of which is about how heat is transferred from high temperature to low temperature. We also looked at how disorder or entropy is needed for a process to take place. So let's look at a couple of examples. We looked at using the Carnot cycle, using the heat engine. We looked at thermal efficiency. So let's look at a couple of examples based on the theoretical aspects that we've looked at. A central power plant rated at 800,000 kilowatts generates steam. So that shows us the place of high temperature at 585 Kelvin. And so that a place of high temperature or otherwise our heat reservoir, as we saw, heat or hot reservoir, 585, and discards it to a river. So this will be, let's say, a place of TH, a place of CH, and then QH, a place of QH, and discards it to a river at 295 Kelvin. So river, so we've seen the steam, then river will be a place of cold reservoir or place of low temperature, a place of so that would be QC. If the thermal efficiency of the plant, this is important, thermal efficiency of the maximum possible value, how much it is discarded to the river at rated power. So we've been, this is one of the formula we've been given in class, which can also be written as to say that we have the maximum amount of efficiency, which is equal to TC over TH. Talking about this maximum amount, it will be clearer as we move on because we need to incorporate the 70%. So substituting what we've got into that, let's first look at the parameters we've been given. So at the river temperature, remember we said that would be the TC. So TC equals to 95 Kelvin. Place of that's your cold reservoir. And we've also said at TH, high reservoir, that is 585 Kelvin. And we've been given amount of work to be 800,000 kilowatts. So plugging what we've got into that equation, then we have thermal efficiency equals 1 minus 295 over 585, which will give us 0.4957. But remember, this, it's written here that the thermal efficiency of the plant is 70% of the maximum possible. So if this is the maximum possible, and it's been indicated to be operating at 70%, then we say 70%, which is all 0.7 times that the maximum value 4957, so which gives us 0.3470. So that's going to be a thermal efficiency. But remember that the question is how much heat is discarded to the river at rated power. So we're looking for QC. So let's look at the other equations we've been given in class. In class, we've shown that we can still relate for the heat engine. The first law of thermodynamics can become this: QH minus QC. So we saw that we can call this, let's call this, so if we take this as a equation 1, we can take this as a equation 2. So let's move on. So I haven't noted that, but remember that in as much that we are looking for QC, we don't have QH. So how do we play around with what we have to get what we need? So let's introduce the other equations. From this QH, we can, from this, we can make QH the subject of the formula. We'll say QH equals W plus QC. Let's call this equation 3. All right, so moving on, another equation we've been given to describe thermal efficiency. So in class we've shown that thermal efficiency equals 1 minus TC over TH, which we've just used. It also equals W over QH. So we'll see, so we can call this equation 4. So we can see there is something common in equation 4 and 3. So in equation 3, the same way that we've made QH the subject of the formula, let's do the same here. We say QH equals W over thermal efficiency. So we call this equation 5. So if we equate 3 and 5, we know 3, equation 3, QH, equation 5, QH. So we can then say QH equals that over that equals this, work done, plus that at the cold reservoir. And then if you make your QC the subject of the formula, we should have QC equals W over thermal efficiency minus W. If you move on to multiply both sides by 1 over W. If you do that, you end up with, so if you do that, we'll end up with QC. Okay, let's try and skip some steps. Okay, let's just do this. QC 1 over W equals to W and times 1 over W minus W times 1 over W. So if you cancel those out, we should end up with 1 minus that into that multiplied by W. So let's call that equation 6. Equation 6. So now let's plug in all the given values into this. So this is QC, which is what we are looking at. So if we plug those in, we have 1 minus, remember we've calculated thermal efficiency, rather we've calculated that earlier on as 0.3470. 0.3470, that's the thermal efficiency which we've calculated earlier on. So if you plug that in, 1 minus 0.3470 divided by 0.3470 multiplied by 800,000, that's the work done we've been given. So if you multiply all those values, our QC should then be 1,005, actually 1 million. If you do that multiplication, 1,050,478 kilowatt, which is also which we can also write as kilojoules per second. 5,478 kilojoules per second. Remember, 1 watt is equal to 1 joule per second. Then 1 kilowatt will then be equal to 1 kilojoule per second. So that is that. So please carefully look at that based on what you've been given in class. So remember, the question is the heat discarded to the river. So if it's the heat discarded to the river, that will be QC. That will be the heat at the cold reservoir. So that's how we got our QC. So let's quickly look at another example. You remember that one of the ways second law of thermodynamics is described is using entropy. So in the lecture slides, this was given as equation 6.7. That is in the lecture slide. So let's look at, and this is the equation we'll use for the next two formula. Is the general equation that relates your entropy. It relates entropy with PV terms. So this relates entropy, change in entropy, to PV terms. And remember, PV terms, talking about this as part is, we call it the PVT relations. And this PVT relations varies for different processes. So PVT relationship for polytropic will be different from adiabatic, from isothermal, and on like that. It will get clearer as we move on. So how do you know what the condition is? By critically looking at the question. So let's look at this. 0.8 kilogram of air. So we've been given mass of air to be 0.8 kilograms. And we've been given R value to be 294. Remember, we've always said be mindful of the unit. And we've also been given CV equals 711 joules per kg Kelvin. Is expanded according to the law. So once you see a law, a PV relationship that has an N value, so that tells you it's an isotropic. So that tells you, a polytropic process. So that tells you it's a polytropic process. It will get clearer as you move on, because being a polytropic process, that's what's going to determine how do we attain to this relationship, the T2 over T1 or V2 over V1. So being a polytropic, but it will get clearer as we move on. But one thing I want you to remember is once we have PV raised to power N equals constant, you're dealing with a polytropic process. Initial conditions, so we've got a P1 is 1.2 megapascal. Remember, megapascal will be 1.2 times 10 raised to power 3 kilopascal. It's critical to ensure consistency to a final pressure. So P2 is in kilopascal. So that's why we converted that to kilopascal, 420 kilopascal. Determine the change in entropy. So we are looking for change in S. And state whether it's an increase or decrease. So we said we are looking for change in S, and then we need to look at what have we been given in this equation 6.7, and what do we need to get? What have we been given? So to know the value of T2, so we need to, in order to solve this, we need the value of T2 over T1. We also need the value of V2 over V1. So those are the values we are looking at. But going back to what we said earlier on, from one of the, if you recall, in chapter 5, please look at the equations we are given in chapter 5. If you recall, in chapter 5, for polytropic equation, for polytropic process, we've indicated that T2 over T1 equals P2 over P1 into the bracket n minus 1 over n. So we've been given that in chapter 5. So I haven't said that. Let's plug in what values we've got. So we've got P2 over V1. So if you plug in P2 over V1, so we say T2 over T1 equals 420 divided by 1.2 times 10 raised to power 3 our n value is 1.25 minus 1 over 1.25. If you solve that, you should end up with 0.35 raised to the power of 0.2, and that should give us T2 over T1 equals 0.8106. So we've been given, so now we know for in this equation we've gotten this, we still need to look for V2 over V1. So we've gotten this, but we still need T2 over T1. Again, for the polytropic process, as we've been given in chapter 5. So in chapter 5, we have this for the T2 over T1. Again, for the P2 over V1, P2 over P1 for polytropic, as provided in chapter 5, we have P2 over P1 equals V1 over V2 raised to power n. So remember, we are looking for this. This is what we're looking for. So let's plug in what we have, but let's start by let's simplify the equation first. We can solve it right away, but I think it's easier for us if we simplify the equation, and how? By simply multiplying both sides, or both, exponential, both sides, exponential by both sides. The exponential, I want to multiply the exponential by 1 over n, So if we do that, we should be left with P2 over P1 equals, so then we have 1 over n equals V2 over, V1, let's go back, V1 over V2. So if we solve that, but remember that the relationship we are looking for, if you go back here, is V2 over V1, not V1 over V2. So we need to further simplify this. So if we further simplify this, it should give us V2 over V1 equals P1 over P2 1 over n, so which gives us V2 over V1 equals, let's plug in the values we've been given. We have our P1 value 1.2 times 10 raised to the power 3 kilopascal, V1 420 kilopascal, 1. Let's use our n value 1.25, and then that should give us V2 over V1 2.3160. So that is our V2 over V1. So we simply go back to the original equation. So we just want to come back here. Now we have this, we've got that. So let's plug in our values. We already have our m, we have our CV values already, and we have our CV values. So let's just plug those values in. So if you substitute into into the original equation, then changing s equals 0.8. Let's put in our units as well, just to ensure that, to see if we are on the right path. Kg times, we have so the equation again, it's mcv ln, okay, mcv. So we have there, so this is our m, this is our cv, 711, that is our cv, joules per kilogram K, multiplied by ln. We have so we have that m, we have remember we have that as well, our m. So we have mcv ln T2 over T1, mr ln V2 over T. So we have that. So ln, so we have our that ln 0.8106, that's our T2 over T1, that's our T2 over T1 plus the other part of the equation. I'm going to write it I'm going to write it here, which will be MR 0.8. We have our R value, which is 294 joules per kilogram K. And then we have it multiplied by ln V2 over V1, which we have here, ln 2.3160. So if we cross out what we've got, kilogram cuts out that, and then from here as well we have those cutting out. Kilogram, we have kilogram cutting all those, so that takes that out. 0.8, remember, this is another kilogram, so we take those ones out, and then we should be left with, if we solve both sides, we should be left with minus 119.44 plus 197.53 joule per Kelvin, and then our answer is 78.09 joule per Kelvin. So the question is the entropy increase or decrease? So it's a positive sign, so it's increase, and this also tells us that the process is going to be feasible. So that's that. Let's look at another question. Still going to use the same equation. Or the first thing we just need to do is identify what kind of process. So here it is spelled out isothermally. So it's spelled out isothermally. Again, let's look at what do we have, what are we looking for. So a mass, we have been given M, 0.12 kilogram. We've also been given pressure, so we have initial pressure and final pressure. So P1 equals 700 kPa. We have P2, which is 100 kPa. So we have all those there, and then we have our T. We have our T, which is equal to 260 degrees C, but remember it needs to be converted to Kelvin, which will be 260 plus 273, giving us 533 Kelvin. And we've also been given, a CP, we've been given a CV. So we have this. Later, then you begin to wonder, why do we need, if CP, why do we need CP there? It's going to be clearer as you move on. So we are looking for this. We've been given this. We need to look for this. We need to look for that. But remember, we've been told the process is isothermal. So if the process is isothermal, what does that tell you? It tells you T2 equals to T1. So this will be 1. Ln 1 will be equal to 0. We'll break it down further as we move on. This also tells us that this is both T1 and T2. So those values are both T1 and T2. Remember, we've not been given R. So that's why we were given CP and CV. So remember, from previous classes, we've shown that CP minus CV equals R. So that is where that's why we need these two values. So if we do that, we're going to get our R value, which is then 14.3 CP minus 10.1, which gives us 4.2 kilojoules per kg Kelvin, kilojoules per kg Kelvin. So we are sorted with this. We are sorted. We have that. We've got this. We've got that. And we are sorted with this as well, T2 over T1. But the question is, how about the V2 over V1? So again, we go back to the equations we've been provided in chapter 5. One of the equations is, which is the general equation for these processes, which is the fact that PV equals mRT. And remember, we also know based on this, P1V1 equals mRT1, and same P2V2 will be equal to mR. We'll see that as we T1, because R is a constant, so we can say R1 or R2, mRT2. So we have that. So we've solved for our R value, but we're looking for V2, we're looking for V1. So let's solve for our V1 first, since we have quite a number of those values given. So our V1, we have our M, which is 0.12 kilogram. We have our R, which we solved here from 4.2, which is 4.2 kilojoule per kg Kelvin. And then we have our T, our temperature, which is 533 Kelvin, which should cut that out. And then we have so that is P. Remember, we are looking for V. I mean, if you were to V1, sorry, you've skipped a step. We V1, if you were to take that here, remember V1 is mRT1 divided by P1. So that is what you're doing here. So all over. So this, the top part, M, so mRT1 divided by P1, which is 700. We have a 700 kilopascal. Another way to look at this is to ensure consistency. We can remember kilojoule. Let me write somewhere as well. Let me put this at this corner to say, remember, 1 joule equals 1 Newton meter. So to ensure consistency, we might as well to ensure consistency, we might as well write 700 kilopascal as 700 kilonewton per meter squared. We know that that's same thing. This is same thing as Pascal. And then this 1 joule, the joule here, this can also be substituted to that. So if we do that, so that we can be able to cancel those ones out. So if we substitute those ones in, so our V1 should then be equal to 268.632. So please try out those units there. I've skipped a couple of steps, but you can try it out and ensure that you're getting what I'm getting. And then that should give us kilonewton meter over kilonewton meter squared, which should give us 0.384. If we cut those values out, kilonewton meter meter squared over kilonewton, this will cut that out, so we'll be left with M and M, so which gives us 0.384 meter cube. So remember, this is an M squared. So that is volume 1. But remember, what are we looking for? V2 over V1. So we've only been given, we've only gotten V1, we still need V2. We can either go back to this, we can go back to these equations here, or we simply just say that in an isothermal process, P1V1 equals P2V2. So if we make V2 subject of the formula, P1V1 over P2, and if you plug in all the values you've got, 700 P1 kilopascal multiplied by 0.384 meter cube divided by 100 kilopascal. That cuts that out. So we should be, and then if you do the division, then we should be left with V2 equals 268.8 divided by 100 meter cube, which is 2.688 meter cube. 2.688 meter cube. So we have, so from this we now have a V2, we have a V1, we have everything we need. So let's plug in into that entropy. Let me first write it out, and then so that we don't have to be going back and forth. So remember, changing entropy equals mCv ln T2 over T1 plus mR ln V2 over V1. Recall for isothermal, as we said earlier on, for isothermal process, isothermal T1 equals T2. So this will become 1, and we know ln 1 is 0. So this is ln 1. Ln 1 is 0. So this equation then becomes, changing S equals mR ln V2 over V1, ln V2 over V1. So we just need to plug in all the values we've got. Let's plug in all the values we've got. We have M 0.12 kilogram. We have our R 4.2 kilojoules per kilogram Kelvin, and then multiplied by, so let me, the other part, so the other part, let me write it here because we don't have enough space there, which will be ln 2.688 over 0.384. So if you cut those ones out, and then you will be left with a couple of values, and then ln, remember V2, so we've put in V values there. If you the ln here should give you 7, so this should give you ln, I mean, if you divide that, it should give you 7, and then if you calculate ln 7, your final answer then of changing S should be 0.9807 kilojoules per Kelvin, kilojoules per Kelvin, which is same as 981 joule per Kelvin, 981 joules per Kelvin. So that is our formula. So if you have any query or anything that needs clarification on this, please don't hesitate to send me a chat or send me an email, and then I'll be glad to assist. But as I always advise in class, I'll advise that you look through these equations together, these questions together in groups, get your colleagues together, look at this. You also have the calculations also in PDF format uploaded on Blackboard, so carefully look at this together, solve it together. But if you still have any issues after that, don't hesitate to chat with me. All the best. Cheers.